Stanford University.
Okay, well, welcome to lecture number 3 of Stanford CS 193P, fall of 2017 and 18 academic year. Today, mostly, we're going to talk about some Swift stuff. Now, you've done your, hopefully, done your homework for the reading, so some of this stuff will be kind of summary, but some of this is really not covered in the reading, so I'm trying to give you the full picture of stuff. That reading is really great, but it is very concise. I know you probably feel like, wow, that was a lot of reading for something that was concise, but it is quite concise, so I'm going to try and cover some of the other stuff. But before I do all that, I'm going to do a little what I call a teaser demo of auto layout, where I'm going to show you how we can make our UI in concentration look good when we rotate the phone or when we run on a little bit different sized iPhone or whatever. I call it a teaser because I don't intend it to teach you auto layout, which is the feature that allows us to do that. It's just to show you what's possible. We'll actually have a whole lecture on auto layout in about 3 weeks, I think. But then after I do that little demo, I'll be back. I'm first going to take just 1 minute to review what you should have learned by what we did last week. And I'm literally just going to read it off a list with quick examples. And you can kind of say in your head, oh yeah, I got that. Or, oh wait, I don't really understand that. And that's a prompt to go back and look at it. Then we'll dive into this long list that you see up here of various Swift things. So let's start with this demo I was talking about, this auto layout demo. What we're going to do here, and I apologize for any technical problems we have here because actually my computer died and I had to put it, this is all brand new computer, so I hope everything's installed properly. But here's the code I think that we had at the end of the last lecture, and you know the UI looks pretty good. We laid it out, but I just did this by dragging these things and using the little dash blue lines to put them in position. And when we run this thing, it looks okay, but only on an iPhone 10 and only in portrait mode like this. If I were to, for example, rotate this iPhone to the side, which I can do in the simulator by going hardware, rotate left or right, you can see that my UI looks like this. My buttons are kind of all jammed in the corner here. I've lost flips. It's down here somewhere. I can't even see it. Still works, but it's kind of off in the middle of nowhere. What we really want is for this UI to spread itself out and fill the whole space that's involved. By the way, you can also rotate your device with the command and the arrows. Okay, kind of a cool way to flip back and forth. All right, so how are we going to do that? How are we going to make our UI expand? Let's go ahead and open up here, give ourselves some more space, and also I'm going to zoom in a little so you can see. Another thing I'm going to do is we're going to be using these blue lines, you know, the dashed blue lines that appear as we move things around as part of this. So I'm going to change my background from black to back to white temporarily, just so that we can see those blue lines and stuff a little better. So I'm just going to go to white. Okay, when we come to run, I'll turn it back to black. So this is purely for during development issues here. So there's really kind of 2 things I need to do to make this work. One is I need to kind of take all those buttons and make them stick to the edges, right? So that when you rotate and the edges get longer and skinnier, they stick. Right now, everything's stuck to the upper left corner. Okay, the upper left corner, you're going to find out next week, is the origin of drawing in iOS. So everything's kind of stuck up to the upper left. And then so when we rotate, it all just goes off the bottom and we can't see it. So that's really what we need to do. But to stick them to the edges, we also kind of need to group them together. Because when the edges pull this group of 12 buttons apart, they all need to kind of share that space. So there's 2 things we have to do. One is group them together. One is pin them to the edges. So we're going to do that with 2 different features in iOS. One, the grouping things together, we're going to do with Stack View. Okay, so Stack View, UI Stack View, is just another class in iOS, like UI Button is a class and UI Label is just another view, in fact. And what it does is it'll take other views, like let's say these 4 buttons, and it'll stack them together. Okay? Now, it only knows how to stack horizontally or vertically. It can't stack 12 of these things in 2 dimensions like this. So I'm going to have to make 3 horizontal stacks out of this group, out of this group, and out of this group, but then I'll take those 3 stacks and stack them vertically, because it's perfectly fine to put stacks inside stacks. All right, and once I do that, I'll have all 12 of these kind of stacked together. And then I can pin it to the edges and they'll stretch out. So how do we make these stack views? Super simple. You just select it here. Let me zoom in so we can really see what's going on here. We only need the top part for now. So I just selected these 4 things. I'm going to go down to this button right here. You see this button, embed in stack? Well, that's what it does. It embeds in stack, and it embedded it. Now, a couple of things. One is it made the buttons as small as it could when it put it in the stack. It has 50-point font, remember, for those emojis, so this is as small as they'll go. It also has no spacing between, but I can put spacing in between by just selecting it. It was left selected after I stacked, and going over here to the inspector, because this stack view, just like a button, can be inspected, right? And you can see it made it horizontal. It kind of noticed my buttons were mostly horizontal, so it picked horizontal. And here's how I set the spacing. I go down here. I'm going to use a standard of spacing. There's a lot of places when you're doing UI design where you can pick in the UI standard value, and it'll pick a standard spacing. Okay, this is a standard spacing between buttons, and you want to use that pretty much as possible. That way your UI will be spaced like other UIs, and it'll feel like we're all on the same page as UI designers across all these apps. Also, I want to make sure that these 4 buttons get equal amount of space. Okay, whatever space I'm given here gets equally distributed, and I do that with this distribution thing here. I say fill equally, right? Alignment just means I fill the whole space. I could have these things being centered or kind of pushed up to the top of the stack, but I'm going to have them fill the whole space. So that's it. So I'm just going to do the same thing with these 2 rows. So this one, go down here, embed in stack. This group right here, embed in stack. Oops, I did it twice there. Now I'm going to select both of these, okay, make them fill equally and standard value spacing. So now I've got 3 horizontal stacks. I'm going to stack these together. I'm going to select them. By the way, dragging to select is really an awesome way to select. I highly recommend you do that rather than trying to click on things, because, by the way, let's say I try to click on here to select this row. Oops, I selected the button inside. I didn't want that. I wanted the whole row. But if I just drag, not control drag, but regular drag here, it selects the thing that I intercepted with my drag. Anyway, so I'm going to select all 3 of these with drag, and I'm going to go embed in stack. It put them in a vertical stack. You notice this time it's vertical because it noticed those 3 things are vertical. If your things are random, it'll pick the one that it thinks is most likely. You can always change it by going here and changing it to the other one. So we have vertical. We also want to fill equally top to bottom here, and we also want standard spacing. So this is great. We got our buttons in this nice grid. Okay, they're all perfectly laid out in this rectangle. Now I want to pin this rectangle to the edges. Okay, so that when the device rotates, or if the device was bigger, like it was an iPhone 8 Plus or something like that, and it was wider, so this would all stretch out. So the way we do that is first I'm going to use those dashed blue lines. I picked up this thing. Okay, again, picking it up, you want to select it first, then pick it up. If you don't select it first and try to pick it up, oops, you might try and pull one of these things out of there. Okay, so be careful about that. All right, so I'm going to use the blue lines. I'm going to put this where it kind of suggests for the upper left-hand corner. You see that? Okay, that's pretty much where the blue lines, that would be the standard spacing from the edges, right? That's what the blue lines are telling you. This is a standard place to put this. Now I need to pin it. And the way we make relationships between views in the UI, like pinning them to each other and stuff, is with control drag. The exact same way that we made a relationship between our UI and our code by dragging to code, we do the same thing between views. So I'm going to control drag from this already selected box here to the top. Okay, so I'm just dragging up towards the top. And when I let go, it's going to say, okay, well, what relationship do you want between that view and the top? And there's various relationships you can have. Like I said, in 3 weeks, we're going to have a whole lecture on these relationships. But at the very top is the one top space to safe area. You see that top space to safe area? The safe area is a safe edge around the screen where you can safely draw without overlapping some other UI. So here it's putting it right under the place where all the cameras and face recognition stuff is all in here. So it's keeping it up below that. Now, if I had other UI on this, like tab bars or title bars or whatever, then the safe area would be inside those. Okay, so we wouldn't be overlapping our titles and stuff. It's really cool. So I'm going to put this top space little pin, so I'm kind of connected it, and you can see this blue line appears right here. Okay, this blue line here, long blue line, it represents that pinning, and I can even click on it. Okay, and when I click on it, look, it's inspectable in the top half here. Okay, and it's just telling me that I'm pinned from the safe area top to the top of that stack view, and we're 0 points away from it. Okay, we want to be right up against that safe edge. That's where the blue dashed lines told me to put it, so that's where I'm going to put it. Now we can do the same thing to the left edge over here, so I'm going to control drag over. This time it says leading space to safe area. Now why do you think that says leading instead of left? Anyone want to guess? It says leading instead of left because some languages, Hebrew, Arabic, they go right to left. Okay, the letters come from the right and they flow out towards the left. In those cases, you want pretty much your whole UI flipped over. So you would want these buttons pinned to the other side because the text on the buttons is going to be coming from the right. Okay, now it doesn't matter with our emojis, but that's why we do leading and trailing instead of left and right. Okay, so I'm going to click this leading space to safe area right here, connect it. I get another little blue thing right here. You see this one? If I click on it, it looks like a little I-beam. It's pinning these two, and it's pinned it with 16 points. You see 16 points? Evidently the blue lines think from the left edge, or the leading edge, you want 16 points. Okay, I'll take that. And then, of course, I can pin to the other side, control drag over here. And now here I didn't use the blue lines for that edge. So here if I say trailing space to safe area, I get an I-beam, but it's huge. Okay, so it goes all the way across like that. And I don't want that. I want it to be the same as the other side, 16 points. So in my inspector right here, this distance is this constant right here, 215 points. So I'm going to change that to be 16 so it matches the other side. Oh, and look what happened. It pinned the edge of my buttons and they spread out, equally, filling equally, because we told we want to fill equally. Okay, so that's pretty cool. Now we have the bottom. Okay, so the bottom is a little trickier because we got flips down here. Okay, so we want flips to be on the bottom and we want this thing to be above flips. So let's work on flips first. Let's just get it so that flips is on the bottom, and we're going to do the exact same thing. So I'm going to grab flips and use the blue lines. Okay, put it in the center and on the bottom. I'm going to control drag to the bottom and say that I want the bottom space to be pinned to the safe area. Okay, so that's good. Now, when I did that, look, I got this yellow and red lines, and I got a warning up here. See this warning? This means there's a warning, and this can be red if you got an error. And if you click on it, it'll tell you what all your warnings are, kind of a quick summary there. And here it says horizontal position is ambiguous for your flip count label. And in fact, it is ambiguous. I never told it where it is horizontally. I pinned it to the bottom, but I didn't say it was in the middle or left or right. Now I dragged it there with the blue lines, but just dragging it with the blue lines just puts it there. It doesn't pin it there. So really what I want with flips is I want it to be in the center. Okay, I want it to be in the center, just to show you something a little different. And to do that, again, I control drag from flips right here to the thing I want it to be in the center of, which is this background here. So I'm just going to control drag to the background. And another option is center this horizontally in the safe area. So I'm going to do that. Okay, now it puts it in the middle. It's still yellow here. Okay, so what does this yellow say? It says the frame for the flip count label will be different at runtime. That's because I have not constrained the size of this flip count label. I've let it be any size it wants. And since it can be any size it wants, it's going to want to be its natural size. Okay, whatever size fits it. Now I can fix this warning down here in this button right here. Okay, this is where all your constraints, all these pinning things to edges is called constraints. We're constraining these views to be in a certain place. And we can just, actually we don't fix it there, but we're going to fix that over here. So remember our document outline that we had over here, this little thing that we hide? If you unhide that and look in the upper right, if there are any of these little warnings, you'll have this little button, and if you click on it, it'll tell you all the problems. So this one is a misplaced view, because this flips is too big for what it should be. So if you click on this little triangle, it'll offer, hey, you want to fix this? And you can fix it by updating the frames, which we want, because we don't care what the frame of this is. The rectangle that encloses it can be anything as long as it's pinned to the bottom and in the center. And we can do other things too, which we'll talk about in a couple weeks. So I'm just going to update frames right here, fix misplacement. Look, it moved flips down. It made the frame around it just barely contain it. Okay? And now the frame around that flip 0 is its natural size. If I run this and do 100 flips so that it has to be bigger, it'll naturally get bigger because its size is not constrained. It's not pinned to anything, only its location. So its size will get as big or small it needs to contain its stuff. And now we see we have no auto layout issues. We have no warning up here. All is well. One last thing we need to do is the relationship between the top of the flips and the bottom of this. Now I could just take this thing up here and control drag between that and the flips, right? That's a good idea. And we could, for example, constrain the vertical spacing between the two. So I'm going to click vertical spacing. There it is. It's this huge bar. I could go over here and change it from 454 to 0 and use all the space here. But that doesn't look very good. I don't really like tall, thin buttons like that. So I'm going to leave this constraint in here, but I'm going to change it from equal, where it has to be equal to 0 with the flips. Also, I probably don't want 0. I want a standard value here, so I'm going to change to standard value difference, okay, this distance. And I don't want it to be equal. I want it to be greater than or equal. So I just want to make sure that these things on the top are always above the flips, greater than or equal. But it doesn't have to be right above it like that. So you don't have to always have these constraints be equal. They can be greater than or equal, less than or equal, kind of relative constraints. Okay? See all this? Now, we can run the app, and this should all work. Everything is kind of constrained to each other. We can actually kind of take a look at it here in Interface Builder, right? Remember this button down here that showed us all these phones? We can say, okay, what's this thing going to look like on an iPhone 8? Here's iPhone 8. We click on it, and sometimes when it does it, you can kind of zoom in or out to get it to redraw. So this is what it's going to look like on iPhone 8. We can look back on iPhone 10, but rotated. So here's what it's going to look like rotated on iPhone 10, and that looks like that's going to look okay. So you can kind of preview a little bit what's going on here in Interface Builder, but there's no substitute for running it. So let's just run it on our simulator and see if it looks like we expect. Right here it is. App seems to be working. Oh, let's go make our background black again. So we'll go back here, background black. Keep our Halloween theme intact. Run out here. Okay, so this thing is working. We can still match things, etc. But now when we rotate, remember Command arrow, look, it lays out the entire UI to fit the space. And it's doing this, it's relaying it out because of those constraints we put it. We constrained this edge to be stuck to here. We constrained this edge to be stuck up here. We constrained this distance to be greater than or equal to a standard distance. We constrained the bottom of this to be a distance down here. We constrained the X position of this to be in the center. We put those constraints on here, and so that when we flip this thing around, it's living with those constraints. Got it? So like I say, this is just a teaser of this constraint stuff. It's a very powerful system for doing these constraints, and we'll talk all about that, like I said, in about 3 weeks. Okay, back to the slides. All right, so here's your brief review of week 1, okay, hyperspeed review. Of course, you know about target action, outlet collections, the card buttons, your flip count label, the touch card, you know about that. You learned all about methods and properties, what their syntax was for all of those things, properties like flip count and tons of methods, all the ones in concentration and card and view controller. You learned about property observing, right? When the flip count changed, we had that did set that would cause the UI to change as well. You obviously learned about arrays, how to put things in arrays, how to declare an array. You learned a ton about model view controller. We went and made the concentration game have a model, the concentration and the card. You learned about value types versus reference types, right? The card, which is a struct, a value type, it gets copied when you throw it around. So when we put them in the array there, we made a copy just by putting it in twice, and it copied it each time it put it in there. Remember that? You learned about initializers. We had initializers both for card and for concentration that each did different things to get themselves initializer. We didn't do initializer for our UI view controller, and we probably never will. Okay, UI view controller's initialization is messy. Okay, so we try at all possible not to use init for our view controller. Okay, and I explained that in your homework that's going out today. You can read about it. You learned about static methods like getUniqueIdentifier and static vars like the identifier factory that we created there. You learned about lazy properties like game, which depended on another property, and so it couldn't initialize. It had a catch-22, and we just made it lazy so that it wouldn't actually initialize until someone asked for it, which would of course be after the thing is all initialized. You learned about for-in loops, which in Swift only work by iterating over what's called a sequence, and we learned that countable range is a sequence, right? 0 ... less than whatever is a countable range, that's a sequence, but also array is a sequence, and string is a sequence of characters. A lot of things are sequences. You can for in over them. We're going to talk about what it means to be a sequence a little later, probably on Wednesday. You learned about dictionary, of course. Our emoji were in a dictionary. You learned about type conversion. We convert types by creating a new thing and using an init with the old thing, like uint32 of an int. Converts an int to a uint32. And of course, you learned a lot about optionals, which I'm sure are all still new to you. And I'm going to talk a lot today about optionals and how they really work and what's really going on with optionals. Okay, so that's your review of week 1. If some of these, if you don't feel like you understand these, probably haven't done your homework yet, then you want to understand these. Very important. Okay, the first 2 things I'm going to talk about here are just a little quick minor things, asides. I mentioned doing a for loop over floats. Okay, so this for I equals 0.5, I less than 15.25, whatever. That's something you might see in C. You can't do that in Swift. Okay, Swift doesn't. It only has for in. That's all it has. But how do we create a countable range or some kind of sequence of those floats? Because 0.5 ... 15.25. That's actually legal to say. But that's only a range in Swift, not a countable range. And that's because we don't know what to count by there. So Swift can't create a countable range. So the way we do that is using a global function called stride. Okay? Stride has from, through, or from and to, depending on whether you're going to include the last thing, and a by, tells what it strides by. Stride is a function that creates a countable range. Okay? Countable range is a generic type, like array is a generic type. It can count over not just ints, it could count over floats, it can even count over indexes into a string, all kinds of things it can count over. And this stride knows how to create a countable range, in this case a closed countable range because I did through 15.25, not to 15.25. It creates one that goes over floats and knows to step by 0.3 there. Okay, so that's how you do floating point 1. You don't have to do that for your homework or anything, but I just wanted to be complete about how we do a countable range for floats. All right, tuples. I try to fit everything into concentration that I can. An example of everything, but I couldn't figure out how to fit a tuple in, even though tuple is a very simple little data structure. And all a tuple is essentially is like a mini struct that has no methods or vars or anything, just has values in it, okay? So it's kind of like structs in other languages, like C structs. They don't have methods or vars or anything, they kind of have vars. They have the data stores and that's it. So, but the tuple is super lightweight and you kind of define everything in line. So here's what a tuple looks like. Here's a tuple X, okay? X is up here is of type tuple. And this tuple has 3 things in it, a string, an int, and a double. And I set its value by just saying equals parentheses the 3 things, okay, the 3 values. Now, what's kind of cool about a tuple as a lightweight struct kind of thing is that the names of the elements is very flexible. You can define the names when you get the values like this. Let, parentheses, word number value equal x. And that actually assigns each of the values of x to the 3 variables, word, number, and value. Okay? So I'm kind of giving the struct elements names as I grab them out. Or you can do the other way around. When I define x, I can say x is a tuple that has a string, an int, and a double called w, I, and v. Then, when I have x in my hands, I can get at w, I, and v with using this dot notation, kind of like it's a var almost in a struct, x.w, x.i, x.v. See, so now I'm declaring the names when I declare the thing. And even if you do this, you can still redeclare the names to be something else by saying let word num val equals x. It'll create those 3 local variables. So it's super flexible on the naming of those 3 things. Usually when we create a tuple, we want to use the second way, you know, the x colon I colon v way, although we probably wouldn't use x, I, and v. Those are terrible names. That's just my slide only has so much space horizontally. Probably word, number, and value would have been better names. Usually we do that, and that's mostly because of documentation. We want people to know what those three things are. If we just declare it like X at the very top there, string int double, people are like, what are those three things? So what's a tuple good for? Well, it's good anytime you want to group some stuff together that's really lightweight, doesn't have any methods or anything associated with it. It's also very good for returning multiple values from a function. Okay? A function in Swift can only return a single thing, but that thing could be a tuple. And now you can return as many things as you want. Okay? So if I had a function getSize, gets a person's size, their height and their weight, let's say I could return a tuple with weight and height. And so when I got it back, I could just x.weight or even just getSize.weight or getSize.height, access it directly. Okay? So that's what a tuple is. I didn't make you read about a tuple in your first reading assignment, but you'll be reading about it in your next one. It's very simple. It's exactly what it seems. There's nothing magical here. There's no hidden things. It's just a simple little struct. Yeah. Sorry?
Does it support indexing?
Do tuples support indexing? You mean like get thing number 1 or get thing number 2? Not really, and we wouldn't really want to do it that way. If we really had something we index, we'd want to use an array there because, you know what I'm saying? It would obfuscate what's going on. The whole great thing about a tuple is you can name each one and let people know what they are. So, all right. Now, okay, that was it for little things. Now we're back to something very important. Okay, this is a big thing. Okay, this is computed properties. So all the properties that you saw in concentration were stored properties. They were just normal vars like you're used to in other languages, right? Like this var foo double. That's a double precision floating point number, and it's just stored in memory, okay? Stored with whatever struct or class it's part of. But it is possible to declare foo like this. Foo double, open curly brace, get with some curly brace, set with some curly brace. Okay? In that case, foo is never stored anywhere. Instead, every time someone asks for foo, it gets calculated with the code inside get. Okay? And every time someone sets the value of foo, this code that's in here inside set gets executed. Okay, so I got a little pointer here. So this is code gets executed when you set. This code up here gets executed when you get, instead of it being stored somewhere. Okay? Now, the set, by the way, that set new value part, that's optional. So you can have computer properties that are only get. We call those read-only computer properties. You can't have ones that are only set. You can have get only, but not set only. Okay? If you had set only, you'd make a function set whatever. Okay? You wouldn't use a var like that. Okay? So why are computer properties important? What do you use them for? Well, a lot of times you have something that is perceived as a property of your struct or class that actually is derived from other state inside of your struct. And when you have that situation, you do not want to have a stored property because you don't want to have the same information in two different vars, okay? Because they can get out of sync, you know, all kinds of problems happen. So you one or the other of them wants to derive itself from the other one. Here's an incredibly good example. Index of one and only face-up card in concentration, okay? That is easily derived by looking at the cards. So you really, we were really kind of bad to have made that a stored property because we have to keep that thing exactly in sync with the face-up state of all the cards. Okay, that's really error-prone way to design. So we could imagine implementing index of one and only face-up card as a computed property where the get just looks at all the cards, and if it only finds one face-up card, it returns that index. Otherwise, it returns nil. Okay? And the set just looks at that index, makes sure that card's face up, and all the rest are face down. You see? So we're just using this computer property to essentially provide this conceptual property, which is the index of the one and only face-up card. That is a property of our game, but it's computed from another one. Everyone get what I'm saying there? Okay? So let's go to concentration and make this change. See what this would look like to use a computed property here like we should have in the first place. All right, so let's go back here to Xcode. Here we go, let's bring our code back up. Get rid of that. Let's go to concentration. That's where this is, all right, so everyone recognize this code, right? This is our entire concentration. Pretty efficient code as is, but it's actually going to look even better once we do this, as you'll see. So here we have index of one and only face-up card. So I'm going to make it computed by putting these curly braces in. As soon as I do that, now it's a computed property. Actually, before we do that, let me show you an even simpler case of this, just to kind of get you warmed up on computed property. Sometimes you have just a simple calculation like this. The number of pairs of cards, which is calculated from the card buttons, right? There might be other times inside our view controller we want to know this number. How many pairs of cards do we have? Okay? So that's kind of a property, and it's derived from this data. So I'm going to take this out of here and have number of pairs of cards be a property. Okay? It's going to be a new var, number of pairs of cards, and it's going to be of type int, and it's going to be computed, so I'm going to have a get. It's going to be read-only, so I'm going to return this. It's not going to have a set. There's not going to be any set right here. And voila, I've created a simple computed property that's read-only. By the way, if you have a read-only property, you do not actually have to have the word get there. Okay? So a read-only property can look like that. Only if you only have a get. If you have the set, you can't do that. Okay, so this is a super simple little one. So now let's go back over here and do the little more complicated one over here. This one does have a get, and it also has a set. And set right here, I put in the slide that it has new value. This is just going to be the local variable inside here that contains the new value that someone set, index of the one and only face-up card 2. A lot of times we don't put anything there. If you do that, it defaults to new value. Okay, that's the name of the locals. There's a special variable in here called new value. But if you wanted to call it something like index, you could do that. It's totally up to you. A lot of times we just say use new value, though. Okay, so getting the index, what do we have to do to calculate the index of the face-up card? So I'm just going to write a little code here. I'll just have a little local variable, say found index, which is going to be an optional int. So I'm going to keep track. I'm going to look through all the face cards and see if I can find one. That's going to be the one I found. So I'm going to use a for loop here and go through all the cards' indices. All right, I'm going to look at each card, and if that card is face up, okay, so I found a face up card, woohoo, I'm going to say if found one is nil, in other words, I haven't found a card yet, and this is my first one, then I'm going to set, not found one, what did I call it, found index, equals that index. Right? So here I'm just saying if I just found my first one, let's remember it. Otherwise, if found index is not nil, that means this is the second face-up card that I've found, because I already found one, and now I found another one. So here I'm just going to return nil. Because if there's two face-up cards, then obviously the index of the one and only face-up card is nil. There's no such thing. And if I make it all the way through this for loop, I'm just going to return the found index, which is either going to have been set to the one card I found, or it'll still be nil from this declaration. Remember that optionals always get this free equals nil when they're declared, right? So it starts out nil, and if I never found one, it'll still be nil, which is right, because that means there'll be no face-up cards. Okay? Everybody understand this simple code right here? And how about the set case? Well, in the set case, I'm just going to go through all the cards and turn them all face down, except for this one that they just set it to, which is going to be new value, right? So I'm just going to go through my cards for index in cards.indices. Great way to go iterate through this countable range of all the indexes in my array. And I'm going to say cards.index.is face up equals false for most cards, but in case the index here, this index, equals the new value of this, then I'm going to set it to true. Okay, so here, this is an expression that's true if someone said index of new of only one and only face-up card equals whatever. If this is the whatever they set, then we're going to have this be true if the card's face up. Otherwise, this will always be false. Everybody got this little code right there? Comfortable with that? All right, that's it. Okay, now that index of one and only face-up card is computed like this from the cards, we do not need to take responsibility for doing things like setting it to nil here. Okay, this is the case where we found two cards, we got two cards that we're trying to match. Well, obviously there's 2 cards, so we had to set the index of one and only face-up card to nil because there were 2, but we don't have to do that anymore because it's always computing that every time we ask. It goes and looks at the cards, okay? And even better than that is this case down here. Okay, this case down here, we are setting the index of the one and only face-up card to be the index. That's because this was the case where there were already 2 or there were none, and now we turn those face down and do this new one. So we're already setting this, and it does all of this. Okay, setting this thing to something already turns all the other cards face down and already sets that card face up, so we don't need any of that code. Okay? So you see how making the computed property makes this code much simpler and straightforward. Okay? Because it really gets at the heart of what's going on. I'm just setting the index of the one and only card to this index that I just clicked on, or I'm just turning this card face up. And the next time someone asks for the index of the one and only face card, it's going to do the right thing. All right, so let's go ahead and run, make sure we didn't break anything, making this into a computed property. Here we go. Hopefully we can still match. Yep, that matches, and the matching is working. And the mismatching is also working. Okay? Everybody cool with computed properties? You're going to see computed properties everywhere in iOS. Okay, very common. Yeah.
When would you use this versus just use a method or 2 methods?
Okay, great question. So when would I ever use this var versus having 2 methods, one which gets the index of the one and only face and one that sets it? Okay, it's all about whether it's perceived as a property. Okay, this index of the one and only face is perceived by us as programmers. It's a property, right? It's a property of the game, is the index of the face of the card. So that's what you would do here. If another way of kind of deciding is if the set, or the get really, does a lot of work, okay, like it's, you know, really crunching on something, you might want to make that a function, just so that people don't think, oh, this is a lightweight little property that I can get. Now, this might seem like a lot of work, but it's actually very, very simple. And later in the lecture, probably on Wednesday, I'm going to show you an even much simpler version of this, okay, when we learn a little bit more about Swift. But it's really not that much work. It's just looking at another data structure. But if you were doing a lot of work, then you probably want to do set and get to make it clear. But otherwise, if it's a var, if it seems like a var, make it a var. Good question. All right. Where is my, here it is, Keynote. Let's go back here. Back to our slides. All right. So the next thing we're going to talk about here is another topic, completely new, access control. Okay, so what is access control? So how many people have worked on a project, an object-oriented programming project, of more than a dozen classes? Okay, like 2 or 3 of you, 4 maybe. So not very many of you. Okay, well when you're working on a very small project like that, you can call any method in any class, whatever. You're probably the only programmer working on it, or maybe you're working on it with a buddy. So you can talk to each other. Okay, but now imagine that you're working for Google, okay, or Facebook, or Apple, or something like that. And this is kind of ridiculous, but let's say you're working on concentration there, and there's a whole other group in another building that does game design, and they write the model, okay? And you are just the UI team for iOS, and so you're only writing the view controller. Okay, well now, you don't want to be calling each other's code just willy-nilly, calling any old method, like you wouldn't want your view controller calling something like index of one and only face-up card if those guys are like, they got rid of that method the next month, and now all your code broke. Okay? Now there are some methods that you have to be able to call over there in their code, and we're going to make it clear which ones those are using access control. So access control is about having keywords that we're going to put into our API, put it on our methods and vars, that says to other groups that we're programming with, yes, you are allowed to call this, I promise not to break this on you. Okay? It also tells them how to use your thing, because the ones that they're allowed to call are the ones that they should be using to use their your concentration game or whatever. So what are these keywords? Well, the first one is called internal. Okay, and these are keywords you put in front of vars and funcs, okay, or even classes and structs. You can make entire classes and structs have access, their access controlled. So the default is internal. This one we never actually type in because it's the default. So all the methods and vars we've done so far in concentration are all internal. Now what does internal access control mean? It means anyone in your app, any object, any code anywhere, can call that method or access that var. So it's pretty much unlimited control inside your app. Now, as we start talking about access control, we have to realize there's really two kinds of programming. There's writing an app, then there's writing a framework, like Apple does, UIKit. Okay, that's a framework, a bunch of objects in there. There's a lot more access control issues if you're writing a framework. So I'm going to tell you what the things are for writing a framework, but we're not going to really pay much attention to them because we are only learning to write apps in this course. So internal means everything in your app or in your framework can access this code. So it's pretty much almost unlimited inside your app or framework. Then there's the three privates. Okay, these are very important. These are the ones you're going to be using all the time. One is just private. That means it's internal implementation to this object. No other objects can call it. Okay? This is a good one to set. It keeps someone in the other group at Google, in the other building, from accessing that code because you're keeping it private. It's your private implementation. Private set is almost exactly the same. It's only for vars. It means that setting this var is private, but getting it is not private. Okay? So you allow people to get the var, access it, but they cannot set it. That's your purview. That's your internal implementation sets it. We'll see a good example of that in concentration. And then there's file private. File private, in a Swift file, you can have multiple classes and structs in there. It doesn't have to just be one class, which is what we've done so far. And file private means anything in that file can access each other, all right? So classes, 4 classes in there, they can all access each other's methods. Okay, that's what file private means. Okay, the other ones are public and open. Those are for framework writers. Public means that people outside the framework can call it, okay? Doesn't make sense for outside your app. That would never happen. So outside your framework. And open means not only can people outside your framework call it, but they could subclass that class, override your methods, all that stuff. So open is like wide open, okay? We don't care about that because we're not doing frameworks. All right, so we're going to focus on private, the various privates. A good strategy to use these is pretty much put private on anything until you're sure, yeah, I want someone else to be able to call this method somewhere. All right, that's by default, you should make things private. So let's look at concentration, what it would look like to put access control on concentration. And pay attention here because I'm going to require in all your homeworks going forward that you mark things properly. I want you to mark things private if they should be private. Okay, because I want to just make sure that you understand what this is all about. So let's go back here to Xcode. Let's start with our view controller. Okay, we have 3 classes, or 3 data structures, our view controller, card, and concentration. So let's start with view controller. So this right here is our model. So would we want our model to be public, to be not private? Well, that depends, actually. Okay, it depends on what your model is and how it works. Often, view controllers' models are public. By public, I mean non-private. Okay, we're inside an app, so forget about public and open keywords. I mean, when I say public, I mean non-private. So a lot of times you do because you give a model to a view controller and it displays it. That's what it does. But that is not the case here. This one wants to be private. And the reason it wants to be private is because the number of pairs of cards in the game is intimately tied to the UI. Okay, the number of cards we have in the UI. So if we wanted to make this public, we would also have to make something public to specify the number of card buttons that we allow. And we don't do that currently. That's something that's in our little scene and interface builder, so we don't do it. So we keep this private. How about number of pairs of cards? Well, this is one where I don't mind if someone asks what the number of pairs of cards is, but setting the number of pairs of cards would be bad. But the thing about this is it's already a get-only property. You can't set it anyway. It derives it from other data. So we're just going to make this private. Not private. We're going to allow people to call this. People who are using my view controller, they can say how many pairs of cards are there. But they can't set it because this is not settable anyway. Okay, so that's okay to make that one public. Same thing, flip count. I think flip count, it's okay for people to get it, but definitely we don't want people setting flip count. That's something we do internally. When the cards are flipped, we increment flip count. So that's private for the setter, but we'll allow people to get the flip count who are using our thing. Our outlets, almost always we have private outlets, okay? Because our private outlets, these things, and even our actions, these are all kind of internal implementation of how we implement our UI. That's what a view controller does. It controls our UI. Definitely something like update model from UI would be private. That's internal implementation. All this emoji business, that's all private. Although you could imagine trying to expose some public API eventually in this view controller that lets someone who's using our view controller specify the emojis they want. Like, you know, this theme required task that you have? You could imagine that there was a way to specify, I want you, Mr. View Controller, to play this game, but I want you to use this emoji as your theme. See, so you could imagine that, something being public. I don't think it would be exactly this API. It would be some other kind of API. I'm not sure what, that would let you set the emoji to use. And we can't really make this public because we actually consume this. Okay, this is a var and we consume it. You've obviously had to deal with that in your homework, I'm sure. And you know, this dictionary we're building on the fly, we wouldn't want anyone messing with it. So I'm going to keep all this private. This is an example of making it private first, and then I'm going to think about what I want to be public. You see the design approach there? All right, let's go look at card. So here's card. Card, definitely, this has to be public. We need to know whether cards are face up. This has to be public. Unfortunately, this has to be public, okay? Because otherwise we can't tell if two cards are the same without that. But these two guys definitely don't need to be public. This whole idea of making an identifier factory, that's purely internal implementation. Okay, so no reason for that to be public. And this, really, I'd love this to be private as well, because a card, it's either face up, it's matched. Whether it's the same as another card, I shouldn't have to look at an identifier to find that. I should be able to just say, this card equals that other card. Wouldn't that be cool? And yeah, it is cool, and we're going to be doing that later in this lecture or next lecture. This is really kind of gross, but for now we'll have to leave that public, because otherwise we can't tell what two cards are the same. Okay, here's the concentration game. This is a really interesting case of private and public, because here is an object, a model that is intended to be used by some UI somewhere. Okay, it's a very intentional use kind of thing. And there's some things we know are private, like this guy for sure. Index of the one and only face-up card. We don't need someone using us to know that. They don't need to know that. And in fact, if we left that public, someone using us would be like, huh, when am I supposed to set that, I wonder? Okay, but it has nothing to do with it. It's internal to our implementation. Cards has to be public, because otherwise the UI can't display the cards. However, cards being flipped up and down or matching, that's my job. So I'm going to make this one private set. Okay, so this is going to be, yeah, you can look at my cards if you want to use concentration game, but I'm responsible for setting the face up and is matched. So you can see this one's clearly private set. Everyone see that? Yeah.
So for that, you can access the cards, but you can't access the methods or properties associated with it?
Yeah, so the question is, when it's like this, does that mean I can access the cards, but I can't access the methods that are on the cards, you mean? And so, no, the methods on the cards, that's over here, those are public. Okay, those are not internal. So I can access those from here. Okay, but you remember that this is a value type, so I can't set is face up and stuff. I can only set that directly in the array, like I'm doing right here. You see, here I'm modifying the thing in place in the array. That's the only way to do it. Well, I can't do this if this is private set. Okay, because it's a value type. So this makes it so this is kind of like it's a let. This is almost makes it like a let for other people other than me, and that so that you can't touch anything in an array when it's a let. Okay, so that's a really cool feature of value types. And remember that array is a value type and card is a value type. So that whole thing is frozen for people who it can't be modified for outside people. But it's for us, it's private set, so we can do anything we want in there, which we have been doing. All right, and then of course, choose card. That's our fundamental public API, so we got to leave that not private. Okay, that's how people do it. And initializers can be made private as well, but this one obviously can't be private because otherwise no one could create a game. All right, so that's it. Everybody got that? Now, while I'm here, I'm going to show you another API protection thing that's different from access control. That's still good, which is using assertions. Okay, everyone know what an assertion is from other languages? An assertion is just a function that you call where you assert something to be true, and if it's not, your program crashes and prints out an error. Okay? And you put it in your code. The asserts are ignored when you ship to the App Store, but when you're in development, it'll be crashing your program, which is good because it takes the debugger right to where the assertion failed. And asserts are a great way to protect your API. For example, look at this API, choose card. What if someone says at index -1 or at index 100 and there are only 12 cards? Okay? That's going to crash somewhere deep inside here, probably like maybe here or something like that. And if I'm the Google guys again, and these guys are in another building, and I accidentally pass -1 here, and I know what's going on, and the crash happens in here, I'm going to need to have this code and look in there, and I'm debugging it. That code belongs to someone in another building. Why would I ever want to be in here debugging it? Instead, the guys in the other building should put an assert here, okay, that asserts that the card's indices contain that index. Okay? If the card's indices don't contain this index, then we're going to crash if we're in development. And so then we want to put some kind of crash message here. I like to put the name of the struct or class and the function, which is choose card. I even like to include the actual arguments that you passed, so you can see what you passed there. And then I give the message. In this case, something like chosen index not in the cards. Okay, so now if someone calls the choose card at -1, it's going to crash right away and put that on the console, and they're going to like, oh, chosen index not on the card. Oh, and I passed -1. You see, they're going to one-stop shop know what they did. And we do a similar thing down here for number of pairs of cards because it's illegal to have 0 or less pairs of cards. You have to have at least one pair of cards. So here, I'm just going to have the assertion be that the number of pairs of cards is greater than 0. And if there's an error, then I'm going to say, yes, I'm in concentrations init, and you passed me this number of pairs of cards right here. And the problem here is that you must have at least one pair of cards. Okay? So you see how I'm using asserts here to kind of protect my API against improper use. Question back there? Yeah.
Can you clarify when you would set it as private? How you would use it?
So when you would clarify when you...
Set it as private?
Oh, so the question is, when would I ever set my init as private? Okay. Well, you might have a complicated object that only creates instances of itself, for example, with static methods or something like that. Or you might have multiple inits, some of which you allow other people to call, but some of which you call internally to create. Okay? You might even have public ones that, as part of their implementation, call the private ones, okay? Because inits can call each other, which we'll talk about on Wednesday. So that's why you might have some private. Okay, everybody cool with access control and assertions? All right, back to the slides. Where are we? Here? Okay, cool one. All right, extensions. So extensions are super powerful. They're kind of like a weapon you want to be careful when you're wielding because you can go crazy with them. And what an extension allows you to do is add vars and functions to other classes, even if you don't have the code to those classes, even if they're in another framework like UIKit or something like that. So you can add vars and methods to int, you can add it to UI button, you could add it to UI view controller, anything you want, okay? So this is a very, very, very powerful feature, and really, I'm sure what's swimming in your mind about the possibilities is nothing compared to the actual possibilities, because there are other data structures that we haven't even talked about that adding an extension to really is powerful, and we'll get to that by end of Wednesday as well, okay? The baseline of it is it's very simple. You just use the keyword extension and the name of the struct or class you want to add a var or property to, and then you just put the thing you want in there. Now, it has one very serious restriction, which is that it can have no storage. Okay? This extension, this code that you're extending, this other thing, it can have no vars that are storage. It could have vars that are computed, but it can't have any vars with storage. Okay, so that does restrict the kind of thing that you can add to a function. Okay, but it's going to turn out that restriction is actually a good restriction. It's not like oh, too bad they couldn't invent it with the storage. You actually don't want storage, and you'll see as we go along why that is. So this feature, as you might imagine, is easily abused. And one of the number one ways it gets abused, and I encourage you not to abuse it this way, is you do not want to add a var or a func to a class that doesn't make sense for that class. Okay? It's a real temptation, for example, for in an int or a string, to add a function that has to do with concentration. Okay? Some concentration-specific method you're adding to string, because it will clean up your code or look nice or whatever. But you really don't want to do that. The only methods and functions you want to add to string are methods and functions that make string a better class. They make it a better string, not that make it so it knows about concentration. Now, it's perfectly possible to add string methods to make it know about concentration. There's nothing really wrong with it. It's just kind of bad design. Okay? So this extensions feature, like I said, is very powerful. Since you're just beginning here, you can think of it at the beginning as just a way to add little utility functions and things like that to clean up your code. Okay? That's the first level of learning about extensions. And so I'm going to show you how we could do that, for example, in concentration. Okay, let's go to concentration and use an extension to add something interesting. And what interesting thing we're going to do is we're going to go to our view controller over here, and we're going to look at this code right here, which is kind of messy right here. Okay, what is messy about this code? Well, okay, all I really want to do is remove a random emoji, and yet I have to have a whole other line of code, and that line of code has this horrendous amount of, you know, changing from unsigned ints to regular ints and all that stuff. So it just really looks bad, and it's hard to read. It's hard to understand what is going on in here. I'm having to do so many type conversions and stuff like that. It's awful. Okay? Really what I'd like to do is generate a random number and put it right here. So what if int, the type int, had a var which gave me a random integer? Okay, that's a very int thing, nothing to do with concentration. It's just int thing. It gives me a random integer. Okay, so we're going to extend int to give back a random integer. Specifically, we're going to make it so that when you ask an int, please give me a random integer, it gives a random integer between 0 and that int. Okay, so if I say 5, I could even say, I'm going to be able to say here, let x equal 5 dot random integer. And I'm going to call this thing arc4random, this var, because I'm going to use arc4random to generate it. And people know the semantics of arc4random, which is a random number between 0 and another number. So this is, I'm going to make it so this will work. And that will give me 0, 1, 2, 3, or 4. Okay? So how do I do that? Extension, int, and then in here, I put this var, arc4random. I have to say what type it is. It's also going to be an int. Okay? It could be a string or whatever, but it's also going to be an int. And I'm essentially going to return all this mess right here. Okay? So I'm just going to cut that out of there. I'm going to return this. Okay? But it's not a random number between 0 and emoji choices.count. It's a random number between 0 and what? Yes. Whoa, I wish I could give extra credit. Or like Mayron, throwing some candy out there or something, because yes, absolutely, it's between 0 and self, because this is a var in int, and so self is the int you sent it to. Okay, so which is really kind of cool. So now, since int can do this, all we need to do right here is we don't need any of this junk up here. Instead of random index, we're just going to say emoji choices.count.arc4random. Okay, so that cleaned up our code a lot. Now, if we were to do something like this and we wanted to be really good programmers, we'd look at this and say, what if self is 0? This is not going to work because arc4 uniform doesn't work. Or what if self is negative? Actually, you know, if self were negative, maybe I could do a random number between 0 and that negative number. Okay? So I might decide, I'm going to say if self is greater than 0, then I'll do this. Else, if self is less than 0, then I'm going to almost do this. What I'm going to do is I'm going to say return minus this, the absolute value of myself. Okay, abs is just a global function that takes absolute value. I could also just say minus self because I'm check to see if it's negative. Or else if self is 0, which would be the else case here, then maybe I'll just return 0. So if you say 0, give me a random number, it gives you 0. So here I've made it so that this never crashes, this doesn't have to be an optional int, and it gives a reasonable response. See? And that's pretty good when you add vars and functions to any class, not even just via extensions. You want them to have good semantics, sensible semantics. You generally don't want them to crash, which is what this would have done otherwise if you sent it to -3. Okay, everyone see how this makes our code a lot more readable? Okay, and how we added something that was sensible for int. All right, that's it. Let's get back to our slides again. Down here, there's arg4 random. Okay, optionals, the dreaded word optionals. So I told you last week that an optional is just a regular old type in Swift. In fact, it's an enum in enumeration. So let's learn about enum, because enum is another thing I wasn't able to work into concentration, although I am going to work it into next week's demo, okay, our drawing demo. But I want to explain what it is so that I can explain what optionals are a little better. So an enum is just like an enum in other languages. Okay? It's a data type, just like struct is a type or class is a type, enum is a type, exactly the same. You can be used in exactly the same places. It's just that it has only discrete values. Okay? Like here's a fast food menu item enum. It can only be hamburger, fries, drink, or cookie. That's it. It can't be anything else besides one of those 4 things. So that's what an enum is. Enums are value types, like structs. They get copied as you pass them around. Okay? Now, enums in Swift, a little bit more powerful than your typical enum because each case can also have what's called associated data or an associated value. So in my fast food item 1, my hamburgers have the number of patties. Is it a double burger or a triple or a single? The fries has the size of the fries, a large fry or small, and I've even used another enum. You see down here at the bottom. I have another, oops, make my thing work here. Oh, there it is. Oh, this is not very good. There, right? Okay. You got it. There it is. So I can use another enum there to do the size of it. And then drink, okay, it has 2 pieces of associated data. Okay, we'll see if we can get this working for that. And if you look at its 2 pieces of associated data, look at the first one. That string, it has no name. These other ones have names like number of patties, size. This one has no name for the first one. It does have a name for the second one. Okay? First one's a string, is an int. Now, the names here don't matter that much because when we extract this information, we're going to be able to give it our own name anyway, kind of like tuples. In fact, these look a lot like tuples, don't they? These little associated datas, they're kind of like a tuples because you can have as many of them as you want. You specify the type, they have names, they're super simple, and they look very much like tuples, okay? So anyway, so this is what it looks like to declare an enum with associated data. Now, how do you assign an enum? So here is 2 variables, one called menu item, one called other item. They are of type fast food menu item. That's their type. And so I set them just by saying fast food menu item dot the case I want. And if it has associated data, I have to provide it. Okay? So the only time you can set the associated data of an enum is when you assign it. It's the only time. Okay, you can't go back later and change this to be a triple because this is fundamentally a double burger. That's what it is. And it's never, you know, if it changed, it would change into a completely different thing. All right, so you don't change the patties. Got that? All right, so when you're setting these values, by the way, of course you can use type inference, but only on one side of that equals. So you could say menu item equals fast food menu item dot hamburger. Okay, which is what was on the previous slide. Or you could say other item of type fast food menu item equals dot cookie. You see, I've just basically moved the type to the other side. But you can't say yet another item equals dot cookie. Swift doesn't know enough there to infer the type on the other side. There could be other enums with dot cookie in it, for example, that you might add later. And then all of a sudden your code won't compile because it doesn't know. So it just says from the start, I don't know what that is. Okay? Now, how do you check what an enum is? You do not use equals. So you don't say if this menu item equals a hamburger, then whatever. Okay, you do not use equals. You use switch. Okay, again, other languages have switch. Switch is more powerful in Swift. This is the basic use of switch right here, where I'm just looking at every possible case that it could be, and if it's that case, I do a little bit of code. So here I'm just printing out what the various cases are. So if it's hamburger, for example, you can see that I'm printing burger. Notice that I'm ignoring the associated data here, which is perfectly fine. You're allowed to completely ignore the associated data when you're checking the state with switch. Now, switch requires you to address every single case. You are not allowed to only look at 2 of the cases. But of course, it's got something that can help you with that. Oh yes, by the way, you see I've taken away the fast food menu item dot in front of hamburger, fries, drink, and Coke, because Swift can infer that. You're switching on a menu item, so it knows this is a fast food menu item, so you can take those away. All right, so if you have one of the cases and you don't want to do anything, you can just break. Break means break out of this switch. Okay, so that's a way to do nothing in this case. So right here, this code would print nothing, because the hamburger case, the menu item is a hamburger with 2 patties, and that hamburger case does nothing, so it would just break out and do nothing. Similarly, if you want to do something for all the rest of the cases, like here I only want to do something for hamburger and fries, actually I do nothing for hamburger, and I do something for fries, and all other cases I just want to print other, then you can use default instead of case whatever. Now, in Swift, you can switch on any type. You could even switch on a string, okay? But if you switch on a string, you'd have to have case A, case B, case C, case AA, case AB. You see what I mean? You'd have to have every case in the world, because you have to do it. So of course, you're going to use default in a string case. Case the couple of ones you want to case, and then you would default the rest. So default is a must. Even for enums, we use it quite a bit. All right, so that's break and enum. So if this were a cookie, then it would print other. All right, multiple line. I just wanted to make it clear that multiple lines of code are allowed. It doesn't have to be one line. That was just because I'm on slides here. I'm trying to make everything fit. And there's no fall through. So in this case, I've got fries. You see up there at the top, fries, large fries there. And so this code would print out yummy fries, and that's it. So I have multiple lines of code in there under fries, 2 lines of code, and it does not fall through and do drink like in other languages. In C, things fall through in switch, but they don't fall through here. There's a keyword called fall through that would let you fall through, but by default it doesn't. Okay? By the way, the same way that it inferred the type all along in here, it can infer that type here as well. I don't have to say size colon fry size enum dot large. I can just say dot large, because it knows that the associated data of fries is a fry size enum. Okay, now what if I want to get the associated data? Okay, so I am interested in it. We do that with switch as well. We just do this little let business. You see the little lets? Okay, in all the cases that you want the associated data, you don't have to do it in all cases, but in the ones you want it, you just say open parentheses, let, and a name of a little local variable for each of the associated pieces of data. Okay, now that little name that you use, so if this were a Coke, see, it would print whatever ounces Coke right there, because it's getting the Coke into brand, it's getting the ounces into something called ounces, and then it's doing that print. This naming, okay, does not have to be the same names as you declared the enum from. In fact, if we look at this Coke one right here, this let brand, remember in the original enum, that didn't even have a name. It was just a string, right? And it had ounces colon ounces. And up here with hamburger, patty count, that was called patties in the original declaration. So again, does this not look familiar to tuples, right? You can rename them when you're getting the information out of them. Okay? So this is how you extract data out of the associated types. Okay? Very simple. And again, it's optional. You don't have to have it there. Also, enums, they're like structs and classes. They can have methods and they can have vars, but no storage. Okay? All the storage of an enum is in which case it is, and that case is associated data. That's it. You can't have any other vars or anything else. So the only vars you could have are computed vars. So see the example I have here, where it's calories, where you'd compute the calories of that menu item, that would have to be a computed type. Okay? You can't store anything in an enum except for the associated data right there. Now, if you're writing a func like this one is included in special order number 1 or number 2 or whatever, if you're doing that, then you can get your own associated data using switch on self, okay? Because I'm inside the enums implementation here, right? So I can switch on self, and then I can get my associated data out so I can calculate my calories, or in this case, I'm calculating whether a hamburger with 2 patties is included in special order number 2, and my code here says yes, because pretty much special order number 1 is a single burger and special order number 2 is a double. Now there's some other interesting things to look at in this code. Notice that fries and cookie right there, okay, right in the middle, fries and cookie, those I combine them into one case, which that's allowed. You can, with commas, you can have multiple going on there. Okay. Also notice in drink, okay, I'm getting the number of ounces in a drink, but evidently in a special order, you can have any drink that's 16 ounces. So I don't care what kind of drink it is. I don't care that brand. So I use the universal I don't care symbol in Swift, which is underbar. Right? Remember we used underbar when we didn't care what the external name in touch card was. We used it in a for loop when we didn't care what the identifier was anymore in concentration. So we can use it here as well. All right? You can modify self in an enum as long as it's in a var. Okay? It's modifiable. You just say self equals some other case. And if that other case requires associated data, you'll have to provide it then. You can say self equals. Now, a very important thing to notice here, if you're going to modify yourself in an enum by saying self equals, that's the only way to modify yourself, by the way, then you have to put mutating in front of the function that mutates you, that modifies self. That's because enum is a value type. And remember, the value types are passed around by copying, but there's copy on write. Swift does copy on write, which means it doesn't actually make a copy until you write. Well, if it's going to do that, it needs to know which funcs might write. So that's what mutating means. It means this func might write. It might change this. Okay? You have to do exactly the same thing in a struct. Okay? If you have a func in a struct and it modifies any internal state of the struct, it has to be marked mutating so that Swift knows to copy on write. Now, not to worry, Swift is super smart. It'll see your code, it'll see you're saying self equal, it'll see that you're modifying your vars in a struct, and it will complain and say, this is protected. You can't write to these things because this is not a mutating func. And you can fix it by making it mutating. And in fact, we'll see that in a little concentration demo in a second here. All right, so that's it for enums. Very simple. So an optional then is just an enum. It looks like this, kind of conceptually. Okay, it's an optional. It's a generic type, like array is. Okay, array can have anything in it. An optional can be an optional int, an optional string, whatever. It's a generic type. And it has 2 cases in the enum. The case none, which is not set, nil. And in the case some, in which case it has some associated data of that type. So an optional int, that would be an int. So that's it. That's what an optional is. Now, an optional, why didn't they just leave it in enum? Well, God, can you imagine every time you want to unwrap an optional, you're having to switch on that thing and case some, get the associated data? That would be so much typing. So all of these special characters we have for optionals, question marks, exclamation points, ifs, double question marks, all that stuff is just so that we don't have to be constantly switching on an optional and doing case this, case that. But that's all it's doing under the covers. It's just syntactic sugar that is doing that. It's not doing anything else. It's nothing special. And so I'm going to show you what all these special characters look like in enum land. And I'm even going to show you a new enum, or a new optional thing, which is this thing at the bottom called optional chaining. And it's where you use a single question mark when you're accessing an optional, that's the one thing we have not seen. And I'm going to show you how that works by showing you in enum land. All right? So declaring optionals, obvious, right? If I say hello, which is an optional string, that's just optional angle bracket string. Okay? And remember that optionals always start out nil, so it's going to start out dot none. Okay? Couldn't be simpler. Unwrapping, also very simple. That's just switching on the thing. So if I have an optional string hello and I say print hello exclamation point to unwrap it, I'm just switching on hello. And if it's in the none case, I crash. And if it's in the some case, then I print whatever the associated data is. Same thing down with if let at the bottom there. Okay, I'm switching on hello. If it's in the some case, I do it. If it's in the none case, I do the else part of the if. Okay? Everybody got that? Implicitly unwrapped optionals are exactly the same. It's just that when I say print hello over here on this side, this print hello, I don't have to put the exclamation point, and it still switches on hello and crashes if it's none. Okay? So that's implicitly unwrapped. Those start out as nil too because they're just optionals. The nil coalescing operator, which is that defaulting thing we used, if you remember in our code, we looked in our emoji dictionary, and if it wasn't there, then we returned question mark. That's just switching on it, and if it's in the case none, then it uses the default, okay, the thing on the other side, and if it's in the case some, then it uses the thing it found, okay? This is optional chaining. So optional chaining, imagine right here, okay, if you look at this little let x equal, imagine that x and the method foo and the var bar, all three of those, imagine those return an optional string. Okay? So we don't know what they do, but they return an optional string. They may or may not return nil. Okay, well what optional chaining there allows us to do is to call those things in sequence, call one, and then when we get the value, call the next thing on that, and when we get the value, call the next thing on that. And if at any time any of those things is nil, we just bail out and return nil. Okay, so the way that works in optional land is we switch on that first x. Okay, if it's none, we return nil, but if it's not, we get the data and call foo. If that works, we get that data from foo and we call bar, and then eventually we set y equal to z that comes out of that. Right? We're just moving across the chain. If at any time any of those things is nil, look at all the case nones. Case none, case none, case none, y gets to be nil, and we're done. We move along. Okay, so that's optional chaining. I made it optional, no pun intended, for you to read about that in your current assignment. I recommend you do because you can make really beautiful code using optional chaining. It's really nice. Okay, so we're going to finish up today with a little review and a look forward to the data structures you use to build an app in Swift. Okay? These are the four: class, struct, enum, and protocol. Protocol is the new one that I'm going to talk about starting on Wednesday. So a class, as we know, supports object-oriented design. It has single inheritance of both functionality and data. You inherit the data, your vars, stored vars get inherited, as well as all your methods and stuff. It's a reference type, lives in the heap. Okay? Now, one thing we didn't talk about, though, is class lives in the heap. When does it get cleaned up out of the heap? And how does that happen? Okay, so people who come from Java, you're probably like, oh, garbage collection maybe? Okay, but no. Okay, Swift does not use garbage collection. It uses a very awesome system called reference counting. And in fact, it's automatic reference counting. It's all handled for you. So how does reference counting work? Okay, we need to talk a little bit about that. So let's take a little detour here. By the way, examples of classes we've seen, of course, are UI view controller, which is our subclass of it, UI button, UI label, concentration, we made that a class. Those are all classes, not structs, right? All right, so let's talk about how this automatic reference counting thing works. It's really simple. Every time, somehow magically, every time that you create a pointer to a reference type in the heap, Swift adds one to some counter somewhere. And every time that pointer to it goes out of scope, or it is not pointing to it anymore, like it was an optional, it got set to nil, for example, then it decrements that count. And when that count goes to 0, it takes it out of the heap instantly. It's not like it's keeping track of it and it's doing any marking and sweeping like a garbage collection. It actually instantly removes it as soon as no one points to it. Okay? So it couldn't be simpler. It's the exact way you would think conceptually to make it work. It's actually quite difficult under the covers to do that. Swift was designed with it in mind from start, so it's an awesome system. You can influence this automatic reference counting a little bit. You can't really control it, but you can influence with these three keywords when you declare a var. Okay, a strong, weak, and unowned. These are the three kind of influencers you can do. The first one, strong, is normal reference counting. So that just means if there's this pointer is strong, and so keep that thing in the heap as long as this is around because I need it, I'm pointing to it. Okay, that's the default. So we never actually type the keyword strong. It's the default, it's always there. It's kind of like internal with that access control. We don't actually ever type that. Now weak, you've actually seen before. Y'all remember weak? It was on the outlets. Okay, when we made that outlet connection, I said, oh, see that weak? I'm going to tell you about that next week. Well, I'm living up to my promise. I'm telling you about weak, okay? What does weak mean? Weak means I'm pointing to this thing in the heap, but I'm only really interested in it if someone else is interested in it. Okay? In other words, if someone else has a strong pointer to it, keep it in the heap. But as soon as no one else is interested in this, in other words, all other strong pointers go away, set me to nil and throw the thing out of the heap. So this is the don't keep that thing in the heap on my account kind of pointer. And notice that it gets set to nil if all the other strong pointers go away. So what kind of type does this have to be? It has to be an optional. Okay? So this weak only works with optional pointers to reference types. Okay? Things that are in the heap. Which our outlets are. If you remember our outlets, like flip count label was a UI label exclamation point. That was an implicitly unwrapped optional. It was an optional, right? Same thing, card buttons was an implicitly unwrapped optional. So those pointers to things in the UI, if for some reason those things left the UI, okay, got removed from the UI somehow, which is possible but rare, then those things would get set to nil. Okay? And you would no longer be pointing to them. And that's what they want, because if there's no flip count label, it's no use trying to update it. Okay? So that's why they make those weak. All right? Now, weak, there's only a couple of places that we use weak commonly. One is for outlets. Another one is delegation. Remember back to my MVC talk, and I talked about the delegation, the data source, and we have these pointers from the view back to the controller where there's that blind and structured communication, all that, which I'm going to talk about on Wednesday. Those pointers are weak because the view, if the thing that they're sending will, did, and should to goes away, well, then they're not going to send those messages anymore, so they want to be nil. Okay? If there's no one to send their messages to, then they just want it to be nil. Okay? They don't want it to be pointing to something. They certainly don't want the thing it points to get stuck in the heap because of it, because they're happy to just not send the messages if that thing wants to leave the heap. Right? Otherwise, we don't use weak that much. Okay? Last is unowned. Unowned is don't reference count this. In other words, I'm pointing to something in the heap, but don't count it as a strong pointer. And I promise I'll never access this thing when it's gone from the heap. Now, this is very dangerous. This is basically trying to outsmart the automatic reference counting system. You're saying you know when it's in the heap or not. And this is really rare. And the one time we use this is to avoid a memory cycle. Okay, everyone know what a memory cycle is? That's where you have something in the heap, and it points to something else in the heap, and that thing points back to it. So they're pointing to each other, keeping each other in the heap, but no one else is interested in them. Okay, no one points to either of them. They only just point to each other. So they're just sitting in the heap for no reason. No one even accessing them. Okay, that's a memory cycle. And memory cycles aren't generally created in Swift normally, but there's one way where they're easy to create, which is closures, okay, which is a feature I'm going to talk about on Wednesday. Okay, and so we will use unowned with closures. All right. Back to our list of data structures here. Of course, there's struct. We know about that. It's a value type. It's copy on write. There's no inheritance of data, but you're going to learn with protocols there is inheritance of functionality. In fact, multiple inheritance of functionality. And you've seen examples of structs, card, array, dictionary, string, character, int, double, uint32. Lots of structs have happened there. And I have here, let's jump over to concentration and see what happens when we make concentration a struct. How about I start off the next one with that, because we're pretty much out of time here. Enum, I'm not going to, so this is the demo, which I'll do next time. And then enum here, we've already just covered, so I'm not going to talk about it. Another value type, discrete values. It also can have the same kind of functionality inheritance. This functionality inheritance that I keep kind of mentioning is done using this last one, which is called protocols. So I'm going to start off on Wednesday with a detailed explanation of what a protocol is. It's fundamental to the design of all of Foundation, all the array, dictionary, string, ints, all those things, fundamentally using protocols everywhere. Massive number of protocols. And it's also fundamental to things like delegation, stuff like that. So it's very, very important, and to round out our full understanding of how to build data structures in Swift. Okay? So we'll start off on Wednesday with that, and I will see you then.
For more, please visit us at stanford.edu.